Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the piece on Edexcel International IGCSE Chemistry Paper 1 CR for January 2023. Let us begin with the first question. Question 1. The diagram shows how the particles are arranged in the three states of matter. So we can see in solid state, there is liquid state and gaseous state. Then they say, use words from the box to identify the changes of state X, Y, and Z. So we're using the words from here. X is moving from liquid to gas. It's going to be evaporation. So the answer here should be evaporating, which we see there. And then Y, it's moving from gas to liquid. That is condensation. So the answer should be condensing, which we see here. And Z, moving from liquid to solid. That is freezing. So the answer should be freezing. In part B, describe the differences in movement of particles in solid and gaseous state. They want us to talk about the differences in movement, not anything else, just movement. So I said solid particles vibrate about a fixed position. Please do not say that solid particles do not move. They do vibrate, but at a fixed position. The gaseous particles move randomly because they have more energy. However, you don't have to put a reason, just say they move randomly. So this brings us to the end of question 1. Let's continue to question 2. Question 2. This question is about gases in the atmosphere. Name the most abundant gas in the atmosphere. This is nitrogen, about 78 to 79%. Then they say, name the noble gas that makes about 1% of the atmosphere. That noble gas is argon, about 1%. Then name a greenhouse gas in the atmosphere. This is carbon dioxide. In part B, a student uses this apparatus to determine the percentage of oxygen in a sample of air. So we see there is wet iron wool, we see a column of air, and there is water here. Rusting of iron requires water as well as oxygen, so the oxygen in air is going to be used up in this rusting process, and then this water is going to come and fill the space that was previously occupied by oxygen. So next they say, this is the student's method. Measure the initial length of the column of air in the tube. Leave the apparatus for 1 week, and then measure the final length of the column of air. The table shows the student's results. Initial length of the column of air in millimeters is that, and the final length of the column of air is that. We can see there is a decrease, and that decrease corresponds to how much space was occupied by oxygen that has been used up in the rusting process. So here they say, state the appearance of the iron wool after 1 week. Iron wool is going to be rusted, so the appearance is going to be red-brown, or you could say orange-brown. Next they say, use the student's results to show that the percentage of oxygen in the sample of air is approximately 18%. To do this, I found the length of the column occupied by oxygen. These are values from the table, and I got 15 millimeters. So, of the total 84, 15 were occupied by oxygen. So 15 divided by 84 times 100 gives me the percentage occupied by oxygen, which is 17.9%. It's approximately 18%. And down here they say, the actual percentage of oxygen in air is approximately 21%. Give a reason why the percentage of air calculated from the student's results is less than 21%. We would expect the difference between these two to result in a percentage which is about 21, but if it's less, it means there was insufficient iron, so not all oxygen was used up. So this brings us to the end of question 2. Let's continue to question 3. Question 3, this question is about alkanes. An alkane has the structure formula, which is that these are 4 carbons and of course 10 hydrogens. Give the missing information for this alkane. The structure formula is that the name of this alkane is going to be butane, because you can see it has 4 carbons, so it's going to be butane. This is the molecular formula, as you can see. The empirical formula is going to be the smallest whole number ratio, which is 2 carbons and 5 hydrogens. And this is a general formula for all alkanes, so I wrote general formula. The next part says, there are 2 isomers of carbon 4 hydrogen 10. State what is meant by the term isomers. Isomers are compounds with the same molecular formula, but with different structure formula. The next part says, draw the displayed formula of each isomer of carbon 4 hydrogen 10. Isomer 1 can be when they are all in straight chain, like 4 carbons in a straight chain. And isomer 2 can be like that, and then we branch off 1 carbon. So this one here is what we see here after filling with the hydrogens, and this is what we see here. One is going to be straight chained and the other is going to be a branch chain. Moving on. In part C, methane reacts with bromine to form bromomethane and one other product. Give the formula of the other product. When this reaction occurs, we can see methane is going to react with bromine, forming bromomethane and hydrogen bromide. So this is a substitution reaction, and the product we're looking for is going to be HBr. The next they say, what is the name of this type of reaction? This is a substitution reaction because Br replaces hydrogen, and then hydrogen replaces the Br on the other side, so it's a substitution reaction. The next part says state the conditions needed for this reaction to occur. We need UV radiation or ultraviolet radiation. In part D, when ethane burns in a plentiful supply of oxygen, carbon dioxide and water are formed. Give a chemical equation for this reaction. So imagine if I've written this equation like this, plus oxygen gives us carbon dioxide plus water. I will begin by balancing carbons. So since we have 2 carbons here, I'm going to put a 2 here. And then I go to hydrogens. Since there are 6 here, I'm going to put a 3 to make the hydrogen 6 on the other side. Then lastly, I have to add up the oxygens. Here we have 4 oxygens, and here we have 3, which gives us 7, meaning 7 oxygen atoms. So here I have to multiply by 7 over 2 to create 7 oxygen atoms on this side as well. So I could have left my answer like that, or I could multiply through to deal away with the fractions, and that is what I did in my answer here. Multiply everything by 2 so that we remove the fractions. So this times 2 gives me that times 2 gives me that times 2 gives me that, and that times 2 gives me that. You could have written with a fraction or without a fraction, you still get the same marks. When the air supplied is limited, incomplete combustion occurs. Explain why a gas formed by incomplete combustion can cause a problem for humans. The gas formed is going to be carbon monoxide. So carbon monoxide will bind to hemoglobin and cause less oxygen to be transported in the blood. So this brings us to the end of question 3. Let's continue to question 4. Question 4. A student investigates the effect of temperature on the rate of reaction between 2 solutions, A and B. When the reaction occurs, the mixture turns from colorless to blue. This is the student's method. Pour 25 centimeters cubed of solution A into a conical flask. Add solution B and measure the temperature of the mixture. Then record the time taken for the mixture to turn blue. The student repeats this method at different temperatures. Give 2 variables that the student needs to keep constant in this investigation. The student needs to ensure that the volumes of solutions A and B are constant, and then the concentration of solution B should also be constant. Moving on. In part B, the table shows the student's results. So we have the temperature that is varied, and we see the time in seconds. They say plot the student's results on the grid. I'm going to plot temperature and then the time taken in seconds. So temperature on the horizontal axis and the time taken in seconds on the vertical axis. So these were my points. I have that, this one here, that, and that. And the next part says draw a circle around the anomalous result. My anomalous result is here. When I gave this to some students to draw, actually some of them ended up drawing through this point like this and went like that. That is also acceptable for those who chose the anomalous result to be here, but the best should be going through this point here. So then lastly they say draw a curve of best fit. Of course the curve of best fit is going to go through these points like that, and that should be your answer. So moving on. Here they say give a reason for the anomalous result. The anomalous result is at 25 degrees corresponding to a higher time, meaning it should actually be lying at this point on the curve where the temperature is higher than 25, actually higher than 30. So here I say the temperature was higher than 25 degrees. The timer was started too late maybe. Next they say use your graph to determine the time taken for the mixture to turn blue at 55 degrees. Ensure you're working on the graph. At 55 degrees, we can see the time taken is 117. So here I said 117 seconds. And next I say use information from the table to calculate the mean rate of reaction at 20 degrees Celsius. Use the expression mean rate is 1 divided by time in seconds. So at 20 degrees Celsius, I came to the graph, draw a vertical line from the 20 degree mark to the curve, and then find the corresponding time. I have 156 seconds. So my mean rate is going to be 1 divided by 156, which is equal to 6.41 times 10 power negative 3 per second. Moving on. In part D, explain how increasing the temperature affects the rate of a reaction. They want you to refer to the particle collision theory in your answer. The particle collision theory deals with kinetic energy. So in this case, the higher the temperature, the higher the kinetic energy possessed by the particles, the more chances of successful collisions occurring, the higher the rate. So I said the higher the temperature, the higher the kinetic energy, more particles collide with each other, so more successful collisions can occur per time. You have to write per time because this is showing you that the rate is faster. The rate therefore increases. So this brings us to the end of question 4. Let's continue to question 5. Question 5. This question is about organic compounds. The diagram shows the displayed formula of methanoic acid, which is that. They say give the total number of atoms in one molecule of methanoic acid. We have 1, 2, 3, 4, 5 atoms, so that's the answer. And then determine the relative molecular mass of methanoic acid. Now, we have 1 carbon, 2 hydrogens, and 2 oxygens. So it's going to be 12 times 1, plus 1 times 2, plus 16 times 2. Adding everything up, I got 46. So my answer is 46. Next, they say, explain why methanoic acid is not a hydrocarbon. Methanoic acid is not a hydrocarbon because hydrocarbons contain carbon and hydrogen only, while methanoic acid contains an oxygen atom as well. In part B, the atoms in methanoic acid are held together by covalent bonds. State in terms of electrostatic attraction what is meant by the term covalent bond. A covalent bond is the electrostatic attraction between nuclei and a shared pair of electrons. Moving on. Here they say, draw a dot and cross diagram to show the bonding in a molecule of methanoic acid. Show only outer electrons of each atom. So we know each carbon has 4 electrons in the outer shell, each oxygen has 6, and each hydrogen has 1. So I position them in this manner. We know methanoic acid is actually like that. The hydrogen with its electron, then carbons having 1, 2, 3, 4 electrons, and then oxygen having 1, 2, 3, 4, and the 2 shared ones from oxygen, while the 2 shared ones for carbon to create a double bond. Remember, each bond has 2 electrons, so if there is a double bond, they're going to be 4 electrons that are shared. Then we have this single bond, which is like that. And then oxygen having 4 unpaired electrons, the 5th here and the 6th here, then hydrogen and its 1 electron. So the lone pairs on oxygen had to be shown to get full marks. Next, they say, calculate the empirical formula of the organic compound with this composition by mass. So we have 52.2% carbon, 13.0% hydrogen, and 34.8% oxygen. So carbon, hydrogen, oxygen. The number of moles are going to be 52.2 divided by 12, which is that. For hydrogen, 13 divided by 1, which is that. And for oxygen, 34.8 divided by 16, which is that. The next step is to divide through by the smallest number of moles, which are these. So that divided by that gave me 1, and that divided by that gave me this. That divided by that gave me 2. So the empirical formula is carbon 2, hydrogen 6, oxygen 1, which we have here. So this brings us to the end of question 5. Let's continue to question 6. Question 6. This question is about elements in group 7 of the periodic table. Part A says, which element is a liquid at room temperature? Now we know bromine is a liquid. This is going to be a solid. That is going to be a gas, and that is a gas, so bromine is a liquid. What color is solid iodine? Solid iodine is dark gray. Next they say, describe a test for chlorine gas. To test for chlorine gas, you can use litmus paper. It could be red or it could be blue, but it has to be damp. If you use damp blue litmus paper, then it's going to be turned red and it's going to be bleached. If you use damp red litmus paper, it's just going to be bleached. In part B, a sample of chlorine containing two isotopes has this percentage composition by mass. So chlorine 35 is 71.2%, and chlorine 37 is 28.8%. They say calculate the relative atomic mass of this sample of chlorine, and they want you to give your answer to one decimal place. So the relative atomic mass is going to be chlorine 35's percentage, which is 71.2 divided by 100 times 35, plus that 28.8 divided by 100 times 37. Adding everything up, I got that. And rounding off to one decimal place, I got 35.6. And this is my answer. Moving on. In part C, a student is given an aqueous solution of chlorine and an aqueous solution of sodium iodide. Explain how the student can use these solutions to compare the reactivity of chlorine with the reactivity of iodine. So the student should add chlorine to the aqueous solution of sodium iodide and then observe, because this is going to cause a displacement reaction to occur and the iodine is going to be produced. So the reaction is going to be chlorine plus sodium iodide gives us sodium chloride and iodine. The key thing here is chlorine is more reactive than iodine, so chlorine is going to displace iodide. The resultant change is going to be that the solution turns brown because we have iodine in the aqueous solution is going to be brown. So this brings us to the end of question 6. Let's continue to question 7. Question 7. A teacher ignites a piece of magnesium ribbon and places it in a gas jar of oxygen. This is the equation for the reaction. Magnesium plus oxygen gives us magnesium oxide. Give 2 observations that would be made during this reaction. So because there is magnesium, a bright white flame is going to be observed as magnesium burns, and the magnesium ribbon is going to be converted into white powder. So when an exam question asks you for observations, make sure you write things that can be visible. So moving on. In part B, the teacher demonstrates a reaction between aluminium and iron 3 oxide. So we have a mixture of aluminium powder and iron 3 oxide powder. Then we have the magnesium fuse. So the teacher ignites the magnesium fuse. A very exothermic reaction then occurs between aluminium powder and iron 3 oxide. The products of the reaction are iron and aluminium oxide. State what is meant by the term exothermic. Exothermic is when heat is released or given out. Next they say, give a chemical equation for the reaction between aluminium and iron 3 oxide. When aluminium reacts with iron 3 oxide, we get aluminium oxide and iron. This is a redox reaction. Aluminium is oxidized and iron is reduced. So here they say, explain why this reaction is a redox reaction. It is a redox reaction because aluminium gains oxygen to be oxidized and iron 3 oxide loses oxygen to be reduced. Moving on. In part C, a student uses this apparatus to determine the formula of magnesium oxide. So we see there is magnesium ribbon here being heated and there is a crucible lid. They said this is the student's method. Find the mass of the empty crucible and lid. Then place some magnesium ribbon in the crucible and find the mass of the crucible, lid and magnesium ribbon. Then heat the crucible, lifting the lid occasionally. After 5 minutes, find the mass of the crucible, the lid and magnesium oxide. The first question says, explain why the student lifts the lid. If you look at the crucible, we have only magnesium, but in the end, we want to have magnesium oxide. That means the oxygen atom is coming from somewhere else, so the lifting of the lid allows for oxygen to come in so that magnesium ribbon reacts with oxygen to form magnesium oxide. So I say to allow the oxygen to enter the crucible so that oxygen reacts with magnesium. Here they say, the mass of magnesium oxide formed is less than expected. Describe what the student should do next to obtain a more accurate value of the mass of magnesium oxide. So if you go back here, all the oxygen atoms that are going to end up in magnesium oxide are going to come from oxygen in the air. So if the mass of the magnesium oxide is less than expected, it means fewer oxygen atoms reacted. Therefore, all we need to do is continue heating as you open the lid to constant mass. So here I said, heat the crucible again while opening the lid and reweighing until the mass of the crucible is constant. So this brings us to the end of question 7. Let's continue to question 8. Question 8. This question is about the oxides of some elements of group 4 of the periodic table. When 5.34 grams of lead 2 carbonate are heated, lead 2 oxide and carbon dioxide are formed. This is the equation for the reaction. So we have that, which is lead 2 carbonate, giving us lead 2 oxide and carbon dioxide. They say give the name of this type of reaction. This type of reaction is thermal decomposition. When metal carbonates decompose, we get metal oxide and carbon dioxide. Next, they say calculate the maximum mass of lead 2 oxide that can be formed from 5.34 grams of lead 2 carbonate. Now, this is the reaction we're talking about. So I have the mass of lead 2 carbonate, and I know the molar mass, so I can be able to find the number of moles. So moles of lead 2 carbonate are going to be the mass divided by the MR, which is 267, and I got 0.02 mole. Now, the mole ratio of lead 2 carbonate to lead 2 oxide is 1:1. So these are the same moles, which are the moles of the lead 2 oxide. And finally, the mass of the lead 2 oxide is going to be number of moles times molar mass, which is going to be 0.02 times the 223, and I got 4.46 grams, which is what we have here. Moving on. In part B, the diagram shows apparatus used to heat lead 2 carbonate. So we have the lead 2 carbonate heated. So they say complete the diagram to show what needs to be added to the apparatus to test that the gas released is carbon dioxide. We'll need to connect a delivery tube to a container containing lime water. And again, you didn't have to put this. You could just put a beaker, but with lime water, provided the delivery tube goes deep into the lime water. Next, they say give a result of the test. The lime water is going to turn cloudy. Moving on. In part C, silicon dioxide and carbon dioxide both contain covalent bonds. Silicon dioxide is a solid with a high melting point, and carbon dioxide is a gas at room temperature. Explain why silicon dioxide has a much higher melting point than carbon dioxide. They want you to refer to the structure and bonding in your answer. Silicon dioxide is a giant covalent structure, but carbon dioxide is just a simple molecule. So giant covalent structures require a lot of energy to break the covalent bonds, which are stronger than just simple molecules or weak intermolecular forces of attraction that are found between carbon dioxide molecules. So here I said, silicon dioxide is a giant covalent structure with multiple strong covalent bonds. These require a lot of energy to be broken, so it has a higher melting point. Carbon dioxide is a simple molecule with only weak intermolecular forces of attraction. These require less energy to be broken, so it has a lower melting point. So the marks were awarded for those keywords that I underlined. So this brings us to the end of question 8. Let's continue to question 9. Question 9. A student uses the reaction between zinc powder and dilute nitric acid to prepare some zinc nitrate crystals. They say complete the equation for the reaction by adding set symbols. Zinc is a solid. Nitric acid is going to be aqueous. Zinc nitrate is aqueous because all nitrates are soluble. And then hydrogen is a gas. Next they say, state what the student would observe during this reaction. Because a gas is formed, we would observe fizzing. So since this was 1 mark, I just wrote 1. You can say either fizzing or effervescence is the same point. In the preparation, the student adds an excess of zinc powder to some dilute nitric acid. State why the student uses excess zinc powder. The student used excess zinc powder to ensure that all the nitric acid is finished, so that the soluble components in the product are only going to be zinc nitrate. Remember, this gas will go off, so the liquid will only be zinc nitrate solution because the unreacted zinc is still going to be in solid state. So use excess of this so that all these soluble reacts, so that we have only one soluble at the end of the reaction. So I say to ensure that all the nitric acid is used up. Moving on. Here they say, describe what the student should be next to obtain pure, dry crystals of zinc nitrate. Filter off the excess zinc, and then transfer the resultant solution into an evaporating basin and heat until crystals form on a glass rod. Then stop heating and let the solution cool for crystallization to fully occur. Pour off or filter any excess liquid, and then pat the crystals dry with paper towels and leave to dry in a warm oven, or you could use a desiccator. Down here they say, the formula of zinc nitrate crystals is that this is hydrated. They say when zinc nitrate crystals are heated, the products are zinc oxide, nitrogen dioxide, oxygen, and water. Complete the equation for the reaction. So we form zinc oxide, nitrogen dioxide, oxygen, and water. Now we can see zinc is going to be 2 here, so I'm going to put a 2 on zinc oxide to create 2 zincs. So since all the nitrogens in the product side are going to end up in nitrogen dioxide, so this is going to be 4. The hydrogens are going to be 12 times 2, which is 24. So this gives us 12 H2O to create 24 hydrogens in total. Now finally, we have to find how many oxygens these are. So the oxygens on this side are going to be 6, which are those, plus 6 here, which are 12. But 12 times 2 gives us 24. So I have to make sure we have 24 oxygens, which is going to be the 12 we already have here, plus the 2 we have here, that is 14, plus the 8 we have here, that is 22, and then the 2 we have here, creating 24, so they should be just O2. So this brings us to the end of question 9. Let's continue to question 10. Question 10. A student uses this apparatus to find the heat energy change when ammonium nitrate dissolves in water to form a solution. So we can see there is distilled water, there is a polystyrene cup, and the thermometer. They say this is the student's method. Add 50 centimeters cubed of distilled water to the polystyrene cup and record the initial temperature of the water. Then add a known mass of ammonium nitrate to the polystyrene cup and stir the mixture until all the solid dissolves. Then record the minimum temperature of the ammonium nitrate solution. They say give 2 reasons why the student stirs the mixture. This is to ensure that faster dissolution occurs and also to ensure uniform distribution of heat. Because you're measuring the temperature change, the temperature has to be uniform so that a correct value is measured. In part B, the diagram shows the minimum temperature of the solution. So if this is 23.4, this is 15, so that is 16, 17, 18, 19. And since there are 5 subdivisions, it means each corresponds to 2 degrees. So if this is 19, 19.2, 19.4. So this is going to be 19.4. And the difference between the two is going to be 4.0 degrees. Moving on. In part C, the student repeats the experiment again using 50 centimeters cubed of water and finds that the temperature change is 3.9 degrees Celsius. Show that the heat energy change Q in this experiment is about 800 joules. They've given us the specific capacity, and they've given us that 1 gram is 1 centimeters cubed. So Q is MC delta T. The mass is going to correspond to the volume of water because the density is 1 gram per centimeter cubed. So 50 times the specific capacity, which is 4.2, times the delta T, which is 3.9, gives us 819 joules. And this is close to 800 joules. Then next they say, the student uses 2.8 grams of ammonium nitrate in this experiment. Calculate the enthalpy change, which is delta H in kilojoules per mole. They want you to include a sign in your answer. We are given the molar mass of ammonium nitrate as 80. So I'm going to use this mass and divide by the molar mass to find the number of moles. So it's going to be 2.8 divided by 80, giving us 0.035. So these are the moles of ammonium nitrate used in the experiment. So delta H should be Q, which is what I calculated here, divide by the number of moles. But remember, this value is in joules. I have to convert it to kilojoules because we have delta H as kilojoules per mole. So to convert 819 from joules to kilojoules, I multiply by 10 power negative 3. So that divided by that, I got this, 23.4, and this is positive because it's an endothermic reaction, temperature decrease. So my answer is positive 23.4 kilojoules per mole. Moving on. In part D, describe a test to show that ammonium nitrate solution contains ammonium ions. To test for ammonium ions, we use sodium hydroxide. So to the sample, add sodium hydroxide and warm, or you could say heat. Then test the gas evolved using damp red litmus paper. If the damp red litmus paper changes color to blue, that is proof that the cation present was ammonium cation. In part E, in another experiment, the student adds anhydrous copper 2 sulfate to distilled water. The table shows the student's results. The initial temperature was 23.2 and the maximum temperature of the solution was 28.5. They say, explain what the results show about the type of energy change that occurs when anhydrous copper 2 sulfate dissolves in water. Because the temperature increased from 23.2 to 28.5, this is an exothermic reaction. So I said this is an exothermic reaction because temperature increased. So this brings us to the end of question 10, as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.